Hi everyone, Dr. Jack Orty here, and today I'll be continuing to try and convince you that free will doesn't exist. And today I'm going to be talking you through sort of anatomical determinism, but also physiological determinism. Now, this strapping young fellow here is a guy named Phineas Gage, and he is holding a metal pole, and that metal pole went through his head and removed part of his brain. And here he is holding it. His name is Phineas Gage, and he is the most famous case study in psychology research. But before I jump into this very interesting story, let me lay down some logical arguments to provide a framework for what we're about to discuss. So here we have the brakes, and I've cut the brake lines in this example, and that has resulted in a crash, right? So by cutting the brake lines, we have a crash. Now from that, we can infer that the brake lines have an important role in stopping. Now, scientists have been doing this kind of research for years. You break a system to learn what it does. Really classic examples is you break a gene, you delete a gene from an organism and look what happens. And based on what happens, you can infer what that gene does. And you can also do this with the brain. Break a piece of the brain, but break a piece of the brain to try and see what that piece does. Now, it's unethical really to break a person's brain, so you have to rely on spontaneous cases of broken brain. And that's where that Phineas Gage guy comes in. So how did he get a metal pole through his skull? Well, he was a rail worker, and part of a rail worker's job is to blow up boulders, to remove those boulders so you can now lay down new tracks on flat land. Now, to blow up those boulders, what they do is they bore a hole, they place some explosives down. Now, if you let that explosives go off, all the energy would just come straight back out of the hole and the boulder wouldn't blow up. So what you got to do is you got to pack in clay and sand on top of that explosives to ensure that the force goes outwards rather than just straight back out of the hole. Now, one day Phineas Gage was packing the clay and sand into the hole and the explosive went off. At this point, that boulder has become a gun and that metal pole is the bullet. Now, the metal pole gets launched out of the hole and it goes through his skull behind his eye. And here's the injury here. It comes out the top of his head and the pole goes clean through. It doesn't get stuck. It just goes boom. It happened a long time ago, so I'm allowed to laugh about it. Anyway, the guy recovered, and the doctors treating him noticed that a chunk of his brain had fallen out, which is unbelievable. But this is where it gets interesting, and this is why it's the most famous case study in psychology ever. Pre-accident, Phineas Gage was a fantastic human being. He was a boss, and his employees described him as a great boss, and his bosses described him as one of the best mid-managers, foremen that they had on the tracks, right? So he was a fantastic human being by all who noted it. After the injury, he became gross, profane, coarse, and vulgar, to such a degree that the behavior was intolerable to a decent human being. Now, the question here is, was Phineas Gage free to do otherwise? Was he free to not be gross, profane, coarse, and vulgar? Or was his actions determined by physical events, such as the removal of part of his brain? Now, you might say that's an old case. What evidence do we have really? Is that good evidence? But we actually have modern examples of this. Now, this is a really sad case. It's horrific. But basically, a male was described as a good human being. He was a loving stepfather and husband, and he was a responsible, functional, normal member of the human society. But relatively quickly, he developed symptoms where he became incredibly sexually lewd and he was unable to inhibit sexual behavior. And he made gross sexual advances on everyone, including, really unfortunately, his 12-year-old daughter. So he developed these pedophilic urges. And when he was arrested, police started to notice symptoms, other symptoms, including loss of vision and headaches and that kind of thing. So they took him to the hospital and they found a giant tumor in his brain. And what's really interesting is when they removed that tumor, his behavioral symptoms resolved. So once his tumor was removed, his behavioral symptoms returned to normal and he became the responsible human being he once was. Was he free to do otherwise while that tumor was in his brain? And if the tumor caused his behavior, doesn't a normal brain also cause your behavior? Now, what's really interesting is if we look at that tumor location on the left here, we can see that it's almost the exact same location in the injury region of Phineas Gage. So this is Phineas Gage's damaged brain, and that's the tumor, and we can see that they are in almost identical positions. And so because breaking that system caused that behavior, we know that the inhibition of their behavior is probably done by that region. In other words, this region of the brain is our brake cable, and we are unable to inhibit these urges. Well, perhaps, it's very complex how the brain works, but we know that this region of the brain is involved in social responsibility, and damage to this brain causes disinhibition and horrible behaviors sometimes, and really just loss of responsibility and understanding and social understanding as well. So we can start to infer functionality of it. But the real question is if physical activities can massively alter the brain, and maybe you're not free to do otherwise given these massive physical extreme cases, then isn't it true that even under non-extreme cases, physical phenomena in your brain are dictating your behavior, right? It's hard to get away from determinism here. If physical changes to your brain can cause certain behaviors, then the regular behaviors must be caused by the physical state of our brain, right? And it becomes a very interesting legal question based on a continuum, right? What if we had the ability to look at every molecule in your brain? Couldn't we find something wrong with murderers? Couldn't we find something different about the brains of pathological people that commit crimes, right? And what happens there? If we are all if all of our actions are caused by the behavior of the brain, what happens to justice as we know it? Now, obviously, I'm not a legal expert here. So it's just something to think about. I'm trying to talk about neuroscience here, but it is very interesting in terms of a legal context there. But you might just say perhaps the broken state of the brain causes broken behavior, whereas you have freedom to do otherwise under a healthy situation. So if we break the brain, then yes, maybe you're not free to do otherwise. But in a healthy brain, there is freedom somehow. I don't understand how that could work. Well, there's another set of experiments that we can do in healthy, normal functioning people to sort of pull back the curtain and see that causality effect going on, that changes in your brain, anatomical and physiological and molecular changes in the brain dictate your behavior. So one piece of evidence here we must understand when we're talking about causality, right, is if the molecular state of the brain dictates your choices, right, then molecular changes must occur prior to the choice being made, right? And that's because of causality, right? So if A causes B, A must occur before B, right? So if the molecular state of our brain causes our changes, if the molecular and anatomical and physiological state of our brain causes our behavior and free will, we should see changes before the choices and free will occur. And that's when these experiments come in by Benjamin Libet. He did these experiments that essentially relied on EEG, which measures sort of field electrical polarity of the brain. It can't tell you direction, but it can tell you whether there are changes in activity in a region of the brain. And they looked at the supplementary motor cortex here prior to a movement, right? So he had the people in his experiments hooked up to machines here that were measuring changes in the electrical potential in the brain, and he got them to do movements and do experiments. So these are the experiments, right? The person is told to just wait, and when they feel the urge to make a movement in their wrist like this, when they feel the urge to do that, when they have made that decision, they're looking at a clock. They're told to remember the time in which they made that decision and then perform the act, right? So the idea is that the thought to clench your fist must occur before the clenching of your fist, fist, and they were told, or the flexion of your fingers really, and they were told to just wait for that urge to naturally come and then do the flexion. And they recorded the muscle contraction using an electromyograph, which looks at changes in electrical activity in your muscles. But they also recorded with EEG the electrical activity of the brain. And this is what they found, right? This is the electrical activity of the brain. Here we have seconds, right? This is the electrical potential of the brain, right? So it's EEG. And this is at the 0 second mark here is when they decided, when they said that they were first aware that the decision to clench their fist had been made. So they're just sitting there and they're like, yes, I have that urge. That is the 0 seconds, right? And what we can see is that there is this up to 1 second beforehand. 1 second's a long time, right? 1 second beforehand, we can start to see changes in the readiness potential. This is called the readiness potential, or this German word that I'm not going to attempt to pronounce. So they saw this change in this readiness potential before the person was even aware that they made a decision, right? So there is clear neuronal activity occurring prior to the awareness of a decision being made, right? And so if that's true, how could a person alter the electrical activity if they're not even aware of it? How could they alter a decision that is coming that they're not even aware is coming, right? And some of the criticisms of this was perhaps what we're measuring here is changes in arousal, perhaps we're measuring a shift in focus to the clock, or something else like that, right? And there was a few criticisms. But what was great was very recently, they repeated the study, but the decision, instead of clenching your fist, was bungee jumping. And they did bungee jumping at 192 meters, but they also did jumping at 1 meter, right? And what they found was the exact same magnitude as the original experiments and the exact same magnitude of an effect between the 1 meter and the 192 meter jumps. Now, if it was about arousal, and you would expect a difference in magnitude between jumping off a 192 meter high platform to just clenching your fist, right? And if it was about focus, imagine what you're focusing on bungee jumping, right? It seems weird to me that looking at a clock would cause such a dramatic difference compared to looking over the edge of a cliff or something like that, right? Which I would say is a much larger signal, right? But even if there is something wrong with this, the principle is still true that there must be molecular changes that occur in your brain prior to your awareness of those molecular changes, because we know that the awareness is downstream of those molecular changes. So perhaps it isn't 1 second, perhaps it's a millionth of a second, but the key is that it must occur prior to awareness. This is a great gift. So this is mapping those changes in electrical polarity of the brain as measured by EEG over time. And so at the 0 second mark is when the person is aware that they are going to jump. That's when they're aware that they have made the decision. And what you can see is that there is this growing negative potential called the readiness potential occurring well before they are aware that they have made that decision. Great, fantastic video right there. Now, we've done loads of experiments using fMRI and other methods to essentially prove that this effect is real. They've put electrodes in the brain to measure neuronal activity directly in human brains prior to making decisions. Now, you might go, how did they get ethical approval for that? But these patients were actually getting part of their brain removed because of epilepsy. And so the placing of needles into the tissue that's going to be removed won't cause damage because they're going to remove that tissue anyway. And what they saw was an increase in the firing rate of this supplementary motor area as prior to them being aware of making a decision, which is fantastic, right? So the neurons are firing, and they get to a synchronous, well, maybe not synchronous, but a threshold of spike firing in that region, which then results in the awareness that a decision has been made. They've since done animal experiments looking at neurotransmitters and noticed that the readiness potential best correlates with dopamine levels in that brain. So how could you have free will if physical and chemical changes are occurring in your brain prior to the awareness that you've made a decision, right? How could you alter these molecular and physical and electrochemical changes in your brain if they're occurring prior to you even being aware of them, right? Your brain has made the decision before you're even aware that you have made the decision, right? And so if that's true, where does free will fit into this image? Where does free will fit into this model? And the answer is it doesn't, right? It's deterministic. It is free will. The appearance of free will is downstream of deterministic molecular, electrochemical, and anatomical processes that are occurring in your brain. And this is fantastic, right? This is fantastic. So in this experiment, right, they basically get told to press the button. They're hooked up to an EEG, just the same, and they get told to press the button whenever they feel the urge, right? And so they do this for quite a wee while. And what they do is they then take that data set, the changes in the EEG signal and the pressing of the button, and they plug that into an artificial neural network, right? And they train the artificial neural network to predict when that person is going to press the button, right? So they've trained it. The person pressed the button, the EEG potential was the information recorded into the artificial neural network. The artificial neural network gradually learned what brain signals best predicts when they push the button, right? Then in the next part of the game, this is fantastic, right? The computer is hooked up to lights on the button, and the participant is told to, when they feel like it, spontaneously press that button. But you are not allowed to press the button if the buttons are lit up, right? But the problem is the computer lights up the button when they detect that you have made the decision to press the button. So here we can see the participant here. He's about to go press the button. Oh, and he goes, I can't. It just lit up. So he got the spontaneous urge to press this button. He goes to do it and he can't because the computer has turned on the light, so you're not allowed to press the button. And so the participant never ends up pressing the button because the computer is able to predict when they've made the decision to press the button, right? So the artificial neural network has been trained of your neural network, your wetware. It has been trained of your neural network to predict when you're going to make a decision. So that kind of goes back to this predictability problem. We kind of claim that humans have free will, unlike rocks, because humans have behavior that's unpredictable. And now we can see, actually, it's just an information problem. If we had given enough knowledge of the state of the brain, humans become predictable, right? That artificial neural network on that computer program could predict your behavior based off just EEG, which is such a coarse measure of what's going on in your brain. If we had a fine tool, maybe if Elon Musk gets his way and we get an electrode planted into our brain that can measure the electrical activity of millions upon millions of neurons precisely in our brain, then we would become very predictable. And in many respects, humans are predictable. That's why I had that random image of two human beings. This artist goes out and he takes photos of sort of fashion trends to show that we all just sort of follow these sheep-like patterns there. But I'm willing to bet, right, even after molecular determinism, anatomical determinism, physiological, electrochemical determinism, you're still unconvinced. You still believe that the squares on this chessboard are different shades of grey, and you still feel and believe that you have free will. And so up next, we're going to have to go through even more convincing with psychological determinism.